Hello everyone, the topic of my case study is the parallel operation of synchronous generators. Moving on to the table of contents, so these are the topics that we'll be covering in this case study. So the synchronization of generators mean that we match the parameters of an oncoming generator to the bus bar system of a power system. Those parameters include voltage, frequency, phase angle, phase sequence, and waveform. So we have that a generator cannot supply to the load if it has unmatched frequency or parameters to the bus bar system. Synchronization can only be accomplished by the means of exciter current, varying the exciter current and the engine speed of the generator. So there are certain advantages of parallel operation. A few of them are listed here. One of them is reliability. So let's say if some part of the power system is not working correctly, then other alternators are still active, which can supply the load, and the whole system does not need to be shut down. The continuity of service is the same point as well. It means that if one of the generators does not work properly, it can be disconnected from the power system without harming the power supply. Another point is that it has expanded capacity option available. So like if the capacity needs to be expanded, then that can be done on the expense of paralleling more generators to the system. And then we have load requirements. So let's say if we have peak load demands, then more alternators can be connected in parallel for high efficiency. So for generators, we want our generators to operate on full load normally to achieve high efficiency. So let's say if we have a small load which is being supplied by a generator which has a much larger capacity, then we are not obviously on our high efficiency. So in the case of a large power system with smaller generators, we would have more higher efficiency as they would be operating on their full loads. So there are certain conditions for paralleling of generators. There's phase sequence, voltage, magnitude, frequency, and phase angle. So frequency of the oncoming generator must be equal to the busbar frequency. The phase sequence of the alternator or on the oncoming alternator must be the same as the phase sequence of the generator is connected to the busbar. The phase angle should uh, be the same, or there should be no phase delay between the alternators and the oncoming alternator, and the voltage magnitude of the oncoming generator should be the same as the voltage magnitude of the bus bar. So here is a simulation that I did for effects of improper paralleling. So we have two generators, source 1 and source 2, 50 hertz initially, and then source 2 to 6 hertz, which would be done here. So we have equal amounts of current flowing through the load. Now, as we change the frequency, we will see huge amount of current into the circuit. So this is highlighted by the fact that if there is a change in frequency, then one generator becomes the sole source of the circuit and then supplies the current to rest of the circuit as well. So as you can see that we have this system which has unequal amounts of current flowing through the circuit due to the change in frequency of one of the generator. It means that one of the generators which has a low frequency now acts as a component of the circuit, whereas the current through the load remains almost the same. This is one aspect of improper paralleling of the system. Now let's frequency of the system back to the normal. Then we can observe that the currents would return to the initial value. So as predicted, the waveforms also change, and there we have it. So moving on to the next point, so there are techniques of synchronization as well. So there are primarily three techniques. The third one, which is currently used these days as well, along the modern techniques. So the three top lamps method is based on the three lamps which go out simultaneously to signify that there is no phase delay and the oncoming generator is in phase with the bus bar system according to the voltage as well. So the next one is the two bright one dark method, which uses two combination of or two sequences L1, L2, and slash L3, which signifies that the oncoming generator has a higher frequency than the common bus bar system. If this the sequence is L1, L3, and L2, then we say that the oncoming generator has a slightly lower frequency than the common bus bar system. However, these two methods are not that useful, and we have a more useful method, which is the synchroscope method, which we use the meter to tell us the difference, if there is any, in the phase delay or phase sequence of the bus bar and the ongoing generator. So the synchroscope meter tells us if there is any difference by the deflection of its needle over here. If there is a huge amount of difference, then it will deflect to that uh, quickly or slowly. But if there's no difference, then it would point straight toward the center. So this is a single scope meter. Then we have parallel operation of two same size generators. Let's say if there are two generators in a bus system, then the total power supplied to the load, the uh, real power, would be the sum of the powers of the generators, individual generators. And then if we have reactive power, which is being applied to the load, then the sum of their powers would be the total power being supplied to the load as well. So then we have frequency power characteristics of synchronous generators. So as we know that individual synchronous generators have this phenomena. If the load is increased on and is increased, then we see a drop in their prime mover speed, which essentially reduces the frequency, electrical frequency, and thus it reduces the power output of the generator as well. So as we can see over here, there's the full load frequency is less than the no load frequency on the full load power demanded by the load. And then we have this relation for electrical frequency, which depends on the mechanical rotational speed and the poles. And then we have this power formula over here, which is dependent on the no load frequency and system frequency. So we can derive from this that the power of the system, power output of the generator depends upon the demanded power by the load itself and the frequency, electrical frequency of the generator itself. So a similar relationship can be derived from the reactive power and terminal voltage, which is discussed thoroughly in the report as well. So here we have a simulation. Uh, we have two synchronous generators which are connected in parallel and are supplying a load. As we can see that the sum of the individual currents is uh, is not exactly equal to the current supplied to the load, but as we can see from the waveforms over here, we will see that the voltages are the sum of the two individual voltage sources, and the current that is being supplied to the load is approximately equal to the sum of the source 1 and source 2 current. So this is all for my side. Thank you, and these are the references that I've used.